Okay, so we're going to start 13.2. Before we do that, we left off with a little exercise to parameterize this particular intersection. So let's set z equal to y and plug that into the equation of this sphere. So what do we get? We get x squared plus 2y squared is equal to 1. And now this is essentially an elliptical equation. So if we set x to be cosine of t and y to be, say, 1 over root 2 sine of t, notice that x squared, let me do this out actually, that cosine of squared t plus 2 times 1 over root 2 sine of t squared. This is actually just cosine squared plus sine squared, and that equals 1. So this actually can parameterize this intersection. And so when since z equals y, so this is a parameterization for that. Now since z equals y, we have x of t being cosine of t, y of t being 1 over root 2 sine of t, and z is also 1 over root 2 sine of t. Okay. Pictorially, this is basically, we have the sphere here, a unit sphere, and z equals y is a plane diagonally that goes this way. So when they intersect, we get some type of what they call a great circle, something like this. And this curve would this corresponds to that. Okay, so that was the exercise for the last problem that we left off. So we're going to jump into 13.2 here, which is essentially about derivatives and integrals of vector valued functions. And we'll start off with just the derivatives part, and probably in the next video we'll do the integral part. So I kind of mentioned this at the beginning of 13.1, but essentially that if you take the limit as t goes to t naught of some r of t, it's just the limit component-wise. So x of t, the limit of y of t, and the limit of z of t of the same components. So hence, it's not hard to see that if you had if you wanted to compute r prime of t naught, which was the limit h going to 0 of r of t naught plus h minus r of t naught divided by h, that would be the same thing applied to each component. You would have limit h goes to 0 of x of t naught plus h minus x of t naught divided by h. Similarly for y, so similarly for y and z. And so what happens is you just get x prime of t naught, y prime of t naught, z prime of t naught. Okay. Pictorially, what's happening is you have a curve in space, something like this, and here's the vector r of, say this is the vector r of t naught plus h, and here is the vector, well, let me just make that, let's call that r of t naught. Let's say we're moving forward in this direction, going this way. So r prime, or r of this vector is r of t naught plus h. And if you take the difference, we're doing this vector minus this vector, so we would get the vector going from here to here. And you can it's a little bit hard to see in three-dimensional space, but the analogous thing happens as with uh, regular curves in 2D, is that essentially when you look at as h goes to 0, that the green line here, the green vector, which is our difference quotient vector, that becomes tangent to the point here, to this point, to the point r of t naught. Okay, so we'll see some examples of it. I think it's easier to see it via an example. The book probably has a better picture as well. But let's do an example. And I think that'll clear things up a bit. So let's take r of t being cosine of t sine of t. Then r prime is just the differentiation in component. So we get negative sine and cosine. And let's just pick a point. Let's say t naught is equal to 0. Then what happens? Well, our r of t is just it's parameterization of a circle in R2. So here is our curve, which is oriented counterclockwise in this particular case. So the vector r of t, r of 0, is actually this vector. R of 0 is this vector. And the tangent vector, r prime of 0, this is 0, 1. And if you draw that, you get a vector right here. So this vector is tangent to the curve. So note that this vector is tangent to the circle. Okay. By the way, how would we write the equation of the line? So let's just find the equation of the tangent line in terms of a vector valued function. Well, you have a base point here. The base point is r of 0. Our direction vector, v, is r prime of 0. So our equation of the tangent line, I don't know what to notate it. Let's see. Let's call it S of, well, that's usually used for something else, to be honest. Let's just call it R tilde of t. This is equal to r of 0, which is the point. So r of 0 plus t times r prime of 0. Right? It's always a base point p plus the direction vector, t times the direction vector. So in this case, it's just 1, 0, because we start at 1, 0, plus t times the vector 0, 1, and this is then 1, comma t. That's the equation of the tangent line in vector coordinates, or in terms of a vector valued function. So r tilde of t. This is the equation of the tangent line. Okay, and that's always the case. And let me maybe write that. So in general, the equation of the tangent line is, well, it's put your base point p plus tv, r tilde of t equals p plus tv, where p is r of 0, and v is, or I should, instead, it may not be at 0, right? It could be at whatever point. R of, I'll call it t0, and this is r prime of t0. I'll just write it as p plus tv, so the notation is not confusing. So start at your base point, which is r of t0. Tangent line at t0 is the following. P plus TV. Let's do one more example here. Let's take R of t to be t 2t and t squared. This is going to be, well, here notice that y is 2x. So we're going to be in the plane y equals 2x, where z is t squared. Z is x squared. So you're going to have a parabolic shape. Z here is x squared. So you're going to get something like this. Here is y equals 2x. So here's the positive y. Here's positive x. You're going to get some, if you just draw that line, in the xy plane, then we have this line passing through that. And on top of that, you're going to have a parabolic shape. So the actual function will, the actual curve will look something that's in that plane. So probably going in this direction. That may or may not be the best looking graph. So let me redraw that one more time here. Let's call this the plane y equals 2x. If we're in the plane y equals 2x, okay, where essentially in this plane you have this parabolic shape. Okay, so you have to place this along the three-dimensional plane or three-dimensional space, and then attach the parabolic shape to it. Okay, I hope that made sense. But try it out. If you're not sure what that looks like, draw this plane, and in the plane draw this curve. And if you can do that, that's your curve. But at this point, I'm not really worried about that. I want to know, say, r prime, what is the derivative? So two questions. What is r prime of t in general? And let's take a point. We want to find the equation of the tangent line at some particular point, say t equals, say, 2. Well, r prime of t in general is 1, 2, and 2t. So if we plug in, and so what do we want to get the equation of the tangent line? We need the base point, which is r of 2, and we need the direction vector, which is r prime of 2. Well, r of 2 itself, this is 2, and then 2t gives us 4. T squared is also 4. And the direction vector is 1, 2, 4. So here you have your base point, here you have your vector. So the equation of the tangent line, r tilde of t, is, what's it going to be? So let me write it this way. It's going to be p plus tv, which when we add it all up, we're going to get 2 plus t, 4 plus 2t, and 4 plus 4t. And that's the equation of the tangent line. Okay, so that's some stuff on taking derivatives, and the key point here is, one is how do you get the equation of a tangent line, and we also want to note that r prime of t is tangent to r of t for all t. Okay, those are the two kind of takeaways. The one thing I want to just talk about a little bit before we stop is, so how does differentiation mix with, say, taking dot products and so forth, taking dot products or cross products? And again, I'm not going to list all of the general rules. They're listed in your book, but I do want to mention a couple of important ones. So some rules here. So let's say we're given r of t and s of t as two vector valued functions. Then, and I want to find d by dt of r of t dot s of t, and I want to find the derivative with respect to t of r of t cross s of t. And it turns out that this actually works out to be exactly what you would think it is using the product rule. So this actually becomes r prime of t dot s of t plus r of t dot s prime of t. And this one is r prime of t cross s of t plus r of t cross s prime of t. So these are two kind of important rules that come up. What I'm going to do is I will prove number 1 here, and I will leave you to try to do number 2. So let's do the proof of 1. So let's say r of t is r1 of t, r2 of t, r3 of t, and s of t is s1 of t, s2 of t, s3 of t. And we want to take the derivative of the dot product. So, well, that's the derivative of r of t dot s of t. That's the derivative of r. I'm going to call it r1 s1 for shorthand plus r2 s2 plus r3 s3. And this is equal to r1 prime s1 plus r2. I'm sorry. Let's do the full. Well, let me write it this way, just as it's going to come out to be nicer if I write it that way. R1 prime plus R1 prime S1 plus, and I'm going to put the second part of the product rule, R2 R1 S1 prime. And you'll see why I'm collecting terms like this. So these two terms right here are the product rule applied to these two terms. And I'm going to do it that way for each of these. So for the second one, I get R2 prime S2 plus R2 S2 prime. So this second set of guys here, that corresponds to these guys. And then plus the derivative of this third term, we get R3 prime S3 plus R3 S3 prime. So why did I collect terms like this? Well, let's look at these three terms together. Those three terms are equal to R1 prime, R2 prime, R3 prime dot S1, S2, S3. And these three guys, those are equal to R1, R2, R3 dot S1 prime, S2 prime, S3 prime, and that's exactly R prime of t dot S of t plus R of t dot S prime of t. Okay, so the derivative of the dot product is the product rule on the dot product. That's what that tells us. So this is the end of the proof. Okay, so I'll leave you here with that. So on the next video, we'll do some examples of integration. examples of integration.